Photons. A photon is a discrete packet of electromagnetic radiation. The energy carried by a single photon is fixed, discrete, and is directly related to the frequency of the light. Photons have no mass. E equals hf equals hc slash lambda. E equals energy of incident radiation, J. H equals Planck's constant, 6.63 times 10 to the power of negative 34 Js. F equals frequency of radiation, Hertz. C equals speed of light, 3 times 10 to the power of 8 ms-1. Lambda equals wavelength, m. Electron diffraction. Louis de Broglie suggested that all particles behave as waves, and every particle has a corresponding wavelength that only depended on the momentum of that particle. This was confirmed in 1927 upon electron diffraction, proving the wave nature of electrons. Particles do not exhibit wave properties all the time, as diffraction only occurs if the gap or obstacle is a similar size to the de Broglie wavelength of the particle. Lambda dB equals h slash p equals h slash mv, where lambda dB equals de Broglie wavelength, m. H equals Planck's constant, 6.63 times 10 to the power of negative 34 Js. P equals momentum, kg ms-1. M equals mass, kg, and v equals velocity, ms-1. Line spectra. Electrons orbit the nucleus of an atom and exist in shells, energy levels, which are a fixed distance from the nucleus. Electrons can occupy one energy level at a time, but not the space in between them. Electrons at higher levels, further from the nucleus, have more energy. A stationary electron has electric potential energy. When an electron is accelerated between two electrodes, some of this energy is converted into kinetic energy. 1 electron volt is the kinetic energy needed to accelerate an electron through a potential of 1 volt. 1 eV equals 1.6 times 10 to the power of negative 19 J. Absorption spectra. Passing white light through a cool gas at room temperature or below, then through a prism or diffraction grating, means dark lines will appear on the spectrum. Emission spectra. Passing white light through a hot gas of 50 degrees Celsius or above by using a heater or passing an electrical current through the gas. Then passing the light through a prism or diffraction grating, bright lines will appear on the spectrum, each with a characteristic color. For a particular gas, the dark lines of its absorption spectra correspond exactly to the bright lines on its emission spectra. Explaining the lines. Hydrogen. Hydrogen has 1 electron that occupies the lowest energy state, its ground state, N equals 1. There are many more energy levels an electron can occupy, N equals 2, N equals 3, etc., and they all have increasingly higher energies. Any electron in a higher level will always fall back to its ground state. Ionization energy is the minimum energy needed for an electron to completely escape the surface of an atom from ground state. How spectra are produced. 1. Photons provide energy for electrons. 2. 1 electron can only absorb 1 photon. 3. If the photon possesses an energy exactly equal to the difference between levels, the electron can absorb it. 4. As a result, the electron now has more energy and becomes excited, so it jumps to a higher energy level. 5. Each jump is equivalent to a specific amount of energy and a specific frequency because delta equals hf. 6. An absorption spectrum is produced due to these frequencies missing from the continuous spectrum. 7. Electrons do not stay excited forever and will eventually drop back down to lower energy levels. 8. As they drop, they emit light in the form of photons with an energy equal to the difference between the energy levels they have moved between. 9. Each drop is equivalent to a specific amount of energy because delta equals hf. 10. An emission spectrum is produced due to the frequencies of these emitted photons.